of earthquake design philosophy. Someone else has started sharing. Okay. I hope you can see the slides. Okay. So today's presentation, I'm sure majority of you may be knowing many details of earthquake resistant design, but we will go slightly into uh, more philosophical issues here rather than actually calculating things and the real design. But this is more of a philosophy, like why we do this and how we do this, rather than actually doing some calculations. So this is what is this presentation is all about. If I earthquake resistance, irrespective of the question when. So we always have minor to moderate earthquakes. If you are sitting in the northeastern part of country, then every month we usually face a 3 to 4 magnitude earthquake. And like I said yesterday, that presently the Mizoram Myanmar border is experiencing a lot of earthquakes, like 20-25 earthquakes have been experienced in past 2 or 3, 4 months only. In the last 1 month, in last 2 weeks, 4 or 5 earthquakes of higher magnitude than 4.5 have been experienced. So severe earthquakes, they do not occur frequently. Now that is the whole, I would say, problem, because we tend to forget about them. But the issue is, though they are not frequent, they usually occur. And when they occur, and if we are not prepared, then we will expect some damage and we will expect some fatalities. Now, generally people ask, those who are not into the technical domain, they generally ask that why don't we construct earthquake-proof structures? So obviously we can construct earthquake-proof structures. There are earthquake-proof structures. I mean, if you look at the nuclear power plants, if you look at the certain huge dams, so they are the structures which are nearest to earthquake-proof structures. They are also not earthquake-proof in real sense, because we cannot predict what size of earthquake can occur. So we can have the maximum magnitude earthquake that has occurred so far is about 9.5, 9.6. But then theoretically we can have even bigger earthquakes. So based on historical seismicity of the region, we can actually design some structures which are earthquake proof. But then there is no upper limit of the magnitude. I mean, of course there is an upper limit, but then we cannot design all the structures located in that region for that earthquake proof resistance. Now that is why, because that we don't know what is the upper limit in that particular region, and even if we know the upper limit, so people say that if we know the strength of the rock, we can find out what is the upper limit of the magnitude of earthquakes. Obviously correct, we can find out, but then like I said, the fault length is so large, so long, that the location of epicenter will actually then decide where we have higher intensity, right? So it's a very tricky thing. The best thing is we design these structures for earthquake resistance, not earthquake proof, and we expect some damage. Okay, now we will discuss in detail why do we expect damage. So this is the earthquake design philosophy. Any structure, any philosophy, we have certain objectives. So these are the design objectives. So the structures, all structures should be able to resist minor earthquakes with no damage. Right now, minor earthquakes are more frequent. Like I said, here in northeastern part of country, we experience every month at least one earthquake of magnitude higher than 4. Okay. Now, if I go back 50 years, I showed you some numbers yesterday. So in last 50 years, we don't have a great earthquake we don't have a great earthquake in this region, but we had smaller earthquakes, several more than magnitude 6, right? But not every month. Okay, maybe once in 3, 4 years, 5 years. So minor and frequent earthquakes, we expect damage, right? If you look at the figure at the bottom, it says that when the earthquake return period increases, we expect more damage. Now, what is the relation between the earthquake return period and damage? The relation is indirect. Now, when I say that we experience magnitude 4 plus earthquake every month, but magnitude 6 plus earthquake every 3, 4 years, at least once every 3, 4 years, that means that the return period of the earthquake, that the number of years, the frequency of the earthquake is higher, of course, for higher magnitude earthquakes, but for smaller earthquakes they occur frequently, so for them the return period is less. So for the earthquakes that have lesser return period, obviously they are smaller earthquakes, and the earthquake design philosophy is such that there should not be any damage to any structure for these smaller earthquakes which have lesser return period. That is why this figure shows here that with increasing return period, the damage increases. Okay, so bigger earthquakes, of course, there will be more damage, but the next philosophy, the next objective of earthquake design is moderate shaking. There should not be structural damage, but then we expect non-structural damage. So if you remember yesterday's presentation, there was a figure that I showed in a boat service area where all the ceiling, non-structural ceiling, it fell, right? It fell. So such non-structural damage are expected under moderate shaking, and under severe shaking we expect even the structural damage, but then no collapse. So when we avoid the collapse, we save life, and we of course save the property. Not only the property which we are talking about, but also the adjoining properties, because the structure, when it collapses, it may collapse over another structure, damaging some other structure. So these 3 points are basically the design objectives in any earthquake design philosophy. So minor earthquakes, no damage at all. Moderate earthquakes, non-structural damage are expected, but no structural damage. Severe earthquakes, we expect structural damage, but then no collapse. Now this is very interesting. The interesting part is when we expect damage, we are saying that damage is okay. So then how do we control? How do we design that after this much damage, structure should not damage further? So that is the beauty of earthquake resistant design. So what are the implications then? Now, these are the implications of the design philosophy. So if you have design earthquake loads which are much less than the maximum expected earthquake loads, right? So design, when we do some discussion on the IS 1893 design base shear calculations, you will come to know that what is the difference between the design earthquake load and the maximum earthquake load, right? But for time being, just remember that these design earthquake loads can be 8 to 10, 12 times, even in some cases 15 times lesser, right? So what I'm saying here, that if there is a building in seismic zone 5, and if the design base shear, design earthquake load for that building is, let us say, X, we can design this building for only 0.1x, right? 1/10 of that. So how is it possible? So that is possible because of many issues that we incorporate in the seismic design. So this is one implication, that the design earthquake load is much lesser than the maximum expected earthquake loads. Okay. Now, level of earthquake protection, it has to depend on the consequences of damage. So, for example, the communication buildings. So then we need to have these buildings used after the earthquakes, right? Because they help in post-earthquake management, so disaster management. So these are the buildings which are required to be designed for higher level of protection. Okay, compared to the ordinary buildings. Now, what are the ordinary buildings? The ordinary buildings are normal residential buildings, which requires slightly lower level of earthquake protection. But then, even in those buildings, we don't expect collapses. Some damage is expected. Okay. Now, if you look at the dams, nuclear power plants, so these are the structures. If there is any damage in these structures, they can cause another type of disaster. So if you remember the Japan earthquake of 2000, I think 15, 16, where you have huge tsunami. Because of that, there was a damage to the nuclear power plant, and still these people are struggling to actually control everything. So these are the structures where we need to provide maximum level of protection. Okay, so the level of protection, it actually depends on what are the consequences of the damage, right? Now, so these are the two implications. One, the design load is less than the maximum expected earthquake load, right? So even if the design load is less, we are saying that structure should not collapse. How is it possible? Next, we are saying that differentiating structures depending on their use, depending on the consequence of another disaster, is equally important. So then, there has to be a proper method to accommodate all these things. So how do we do this? And if we try to all these things, how do we ensure the earthquake safety? So this all is done because we rely on inelastic response of the structure. So remember, this is not elastic design. So that means we are not saying that the structure will not damaged. We are saying that structure will get damaged. That means there will be some non-linearity. Damage means either the concrete has cracked, and the concrete will crack only when its strength is reached, right? So that means that the material has entered into non-linearity. The steel bars may also yield, which is again a non-linear response. So we are not only relying on the linear elastic portion of the material stress strain curve, right? The Hooke's law, we are way beyond that now. And then if we can rely on this inelastic response, then we can actually achieve these. So for that, we need to have very good reinforcement detailing, very good earthquake resistant construction, very good material quality. Only then we'll be able to actually do this. So now I come to this Indian seismic code equation. So this IS 1893, we have this equation, this method, which gives you the design base shear. Now you may ask, what is the design base shear? See, the earthquakes are nothing but the release of energy, and this energy is released in terms of different seismic waves. So when these waves arrive at the structure, arrive at different region which are far off from the epicenter or maybe near epicenter, they impart this energy to the structure. Okay, now this energy has to be dissipated. It must go somewhere. Once it reaches the structure, it must go somewhere. So where will it go? So most part of the energy that is released during the earthquake at the focus is actually released in breaking the fault itself, in that plate movement itself. Huge amount of energy is released there, but then only the small amount of energy that reach the structures, that has to be dissipated. Now this is dissipated by deformations in the structure, by damage, by crack patterns, crack formation, or if you have certain additional devices like dampers, right? Passive energy dissipation systems, as active energy dissipation systems. So this energy is dissipated in the structure, and again in the soil, in the movement. So anything that moves, anything that resists, it dissipates the energy. Okay, so this energy, which is actually transferred to the structure from the ground, during the earthquakes, it is actually transferred in the form of acceleration. So the structure accelerates when these waves are transferred to the structure. Now this acceleration, if you remember Newton's law of motion, if we multiply this acceleration with mass of the structure, so acceleration that is coming to the structure multiplied by the mass of the structure, that gives you the force. So this is the force that is acting on the structure because of the earthquake. right? And this is a very simplistic way of explaining what is earthquake force. The reality is slightly more complex, but we are assuming that the whole structure is a single degree of freedom system and it has only one mass, it has only some stiffness. So that is how you can actually define the force. Now this force which is acting at the base of the structure is called the design base shear in a very simplistic manner. Okay, so how to calculate this base shear? Like I said, it is not as simple as just I told you that you just simply multiply the mass with the acceleration, but it is slightly more complex in the sense that there is a soil. How do we know that this is the acceleration at the bottom of the structure? It's very difficult to know. I mean, even if you have some accelerometers installed at the base of the structure in the soil, on the rock, still at different locations you will have different accelerations, right? Even in the same city, because the soil profile is different. So it's not an easy question to answer like what is the acceleration. So there has to be certain method which gives us this acceleration. So the Indian code has actually given this equation which I call the magic equation. Okay, why magic? Because it is so simplistic, and you will most of you must be knowing about this, but still for the sake of discussion I am discussing it. So if you look at the parameters that are there, look at the various terms that are there in this equation, it is really simple. So the design base shear denoted as VB is given by this AH, which is the design horizontal seismic coefficient, and multiplied by the seismic rate W. Okay, so in a very simplistic way, this is basically some sort of acceleration AH multiplied by some sort of mass. Okay, so we multiply acceleration and mass, we get some design force. But then this is not exactly the same thing here, but in a simplistic manner. Now, how do we calculate this AH? Because it is not easy, like I said, there's so many parameters, distance from the epicenter, type of soil, type of structure, so there are many things. So for that also, the Indian code has given us this equation, which is also very simple. So it is, AH can be calculated as this, Z by 2, I by R, and into SA by G. Now each of these parameter is very important and it governs the design force, right? It actually controls how much force is how much is the design force for that structure. So it is very important to calculate all these parameters precisely, right? So the first term in this equation is the Z. So Z is the seismic zone factor. Okay, so it depends on the location of the structure. Like I said, there are 4 zones in India: zone 2, zone 3, zone 4, and zone 5. And if you remember yesterday's number, the numbers were 0.36 for seismic zone 5. And what was the number for seismic zone 2, Jabalpur? It is only 0.16. Okay, so now you can imagine if you substitute that Z value here, for Jabalpur it is only 0.16 and for Guwahati it is 0.36. You can see how much difference will be there in AH calculations. Okay, more than 2 times for the same structure. So that is the first term. The next term is I. I is the importance factor, so it depends on the function of the building. So like I said, the consequences. If there is a consequence of another disaster, of some management of the disaster, so what type of structure is that? Is it a school building? Or is it a communication building? Is it a power plant? Or is it a hospital? Or it is a normal residential building? So depending on function of building, we have to actually define this I. So our code has given several values of I for different types of structures. Now, if you look at this equation AH, I is in the numerator, right? So when you use value of I more than 1, what you do, you increases AH, and then in turn you increase the value of VB. Okay, so higher value of I, you have higher value of design base shear. So for important structures, you will have higher value of VB. The next term is the R value. Now R is response reduction factor, and it is the most interesting factor in the design code in IS 1893. It is also the most complex factor in IS 1893. I will explain why is it most complex. But you don't have to worry much. You just have to find out what type of structure you are designing, and the code directly gives you the value of R. Okay, nobody wants you to actually determine R depending on the parameters on which it depends. So these are the parameters on which R depends. The material properties, the section properties, what is the reinforcement detailing, and some other. So we will discuss about this. Now, the most important part here is in this equation, you can observe that R is in the denominator, right? It is below. So when you increase R, what do? You reduce the value of AH, right? And which in turn reduces the value of VB. Okay, so for a higher value of R, the design base shear will be less. So that means if you have a structure for which you can increase the value of R, that is beneficial, because doing that you can actually reduce the design base shear, and that is what is the whole game of this, relying on non-linear properties of the structure, non-linear response. So we try to increase the value of R, right, so that we can reduce the design base shear. Okay, so we will discuss about it in detail. The last term is SA by G. So it's basically design acceleration coefficient. So this comes from the ground motion directly. Okay, so and we normalize this design acceleration coefficient with respect to the peak ground acceleration. Okay, so like I said, it depends on the ground motion, depends on the structure also. So it's a function of natural period Tn, which in turn is a function of mass and stiffness. Okay, so we'll discuss what is SA by G also later. But then here you simply multiply Z by 2 and I by R with SA by G. Okay. Now you may ask, what is this 2 in Z by 2? Why? What is 2 doing there? Because if you look at Z, it doesn't have any units. I, R, no units at all. SA by G is normalized with acceleration, right? Again, it has no units. So then this whole AH has no unit. When you multiply this AH with W, which has a unit of weight, so then VB has a unit of weight. That means you will get VB directly in Newton or kilonewton, depending on what is the unit of W. Okay. So what is this 2 doing there? So the role of 2 is very interesting. Now, if you want to design your structures for a low level of shaking, I mean, of course, the shaking is governed by the seismic zone factor, zone 2, 3, 4, 5. But then for some important structures like bridges, you can design the bridge for a functional level. Functional level in the sense that for regular small earthquakes which are of magnitude 6, 5.5, 6.5, or you have to design these bridges for a very high level of earthquake shaking, let us say 8.5, right? So if you simply use this equation, it is difficult to actually design any structure for 2 different levels of earthquake safety, right? Because the equation is the same. So for lower level of earthquake safety, for functional level, people use this Z by 2. And for safety level, which is higher level of earthquake safety, people remove this 2 and they simply use Z, right? Otherwise in Jabalpur, let us say, where Z value is 0.16, if you use this 2, this whole number Z by 2 becomes 0.08 only, okay, which is very less. So that is why this 2 is there. So for safety level, for higher level of safety, structural safety, you can actually remove this 2. Okay. Now you can now imagine that Z is given in the code directly in a table, I, R and SA by G. So everything is given in the code. You don't have to go to site. You don't have to do much calculations. Only small calculations. You can actually find out all these values. And weight of the structure, seismic weight, you already know. right? So that is why I call this the magic equation. It is so simplistic that you can straight away calculate what is the design base shear that is acting at the base of the structure. Okay, and this, since this AH has no unit, so the design base shear is only a fraction of seismic weight of the structure, right? Now, if I give you some numbers, let us say I can give you Z, I, R and SA by G, and obviously no units anywhere, so AH is only a number. Now, how big this number can be or how small this number can be, it depends on where the structure is, Z. It depends on how important the structure is, I. It depends on how you are designing, how do you want to design the structure, what is the ductile detailing, how is the reinforcement, how is the section, that is R, and what are the natural properties of the structure, T, N. Because of, depending on that, you can get SA by G. So what I mean here is AH is just some number. And if you remember the previous slide where I said that this design base shear, it is only a fraction of the actual uh, 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 earthquake force acting on the structure, right? So this AH will be anywhere between 0.07 to 0.15, 0.16, depending on all these parameters. So that means 0.07 times the weight, or 0.15 times, 0.18 times the weight. Okay, so that means you have to design the structures for only 7%, 8% to maybe 15% or 18% of the weight of the structure, right? So this is very interesting. Even without doing any calculations, depending on which zone you are in, depending on what type of structure, so with little bit of experience, you can very easily say that the calculations are correct or not. Seismic zone 5, you are designing a hospital building, and if someone tells me that the design base shear for a hospital building in Guwahati is only 8% of the weight of the building, I'll straight away say that it is not correct. Because I know that this AH will increase because I is more, R is of course there, but then Z is also more, and hospital is a big building, so I can say that it has to be more. So 8% to 15%, that is the range in which most of these structures are actually designed. So this is so simplistic, right? You just find out the weight of the building and the lateral design base shear will be on an average 10%, 12% of the weight of the structure. Okay. So let us see, I mean, in order to understand the design philosophy more, let us see what is this IS 1893 and why, how we actually develop that code. Now, the most interesting aspect here is the seismic zonation map, because it tells you which region falls under how much seismic hazard. So earthquake zoning map is basically, it was developed considering the maximum intensities at each location. So depending on the past earthquakes. Okay, and if you look at these annexures A, B and C, you will find that these details are there. So it all depends on the seismicity of the region, the past earthquakes. Depending on that, we have actually keep on modifying the seismic zoning map. Now, how do we modify? I am actually in that committee CED 39 of Bureau of Indian Standards that takes care of that, develops and modify all these seismic codes. So in India, we have very poor instrumentation. We don't have much accelerometers located at, even in seismic zone 5, forget about 4 and 3, there are some instrumentation, but not up to the acceptable level. So because of this poor instrumentation, we don't have much data. Okay, and in absence of data, we have to rely on the historical seismicity of the region. So therefore, if you look closely how our seismic zones are, how distributed are these zones, it will be interesting. So for example, those of you who remember, there was a Latur earthquake in 1993 in Maharashtra. Before that earthquake, that zone was not regarded as a high seismic zone, right? But now it is regarded. Similarly, there was an earthquake in Koina near that Koina Dam. So after that earthquake, we actually increased the seismic zone of that region. So this is what we do, because we are very poor in instrumentation so far. Okay. Now the seismic zone map is actually associated with 1964 MSK intensity scale, and like I said, there are 4 seismic zones. Initially, before 2002, there were 5 seismic zones. So, but then later, when we had so many intraplate earthquakes, I mean, in between, Jabalpur earthquake was there, then Latur earthquake was there. So we actually removed seismic zone 1. Okay, now we start from seismic zone 2. Even the areas like Tamil Nadu, they are now in seismic zone 2. So the provisions are intended for earthquake resistant design of normal structures. Okay, if you have some special energy dissipating devices or some special type of structures, you cannot actually expect that this code will give you the design forces for those structures. Then you have to use the specialized literature. It provides, this code provides the minimum design forces for earthquake resistant design of special structures. So even with these structures, you cannot design for the levels given, levels lower than the level given in the code, right? So this code will govern the minimum design force. Whatever you do, whatever external system you apply, but then these are the minimum levels. But the actual levels can be different. So IS 1893 was published in 1962 first, and then we have revised it 6 times, right? And another revision is already in process. So about last month there was a meeting where we found that there are many concerns in this 2016 version. So slowly, maybe within a year, will have another round of another version of this code along with the commentary. So this commentary will tell you what is the meaning of different codes, different clauses in the codes, and why this clause is there. Currently, it is missing. Now let us see what is the nature of earthquake design problem and why we have to treat it differently. So if I just compare the same structure resisting the earthquake load versus resisting the wind load. So this is the response. The response will of course be dynamic because both the loads are dynamic in nature. They will be cyclic because the structure, when it vibrates, it is cyclic vibrations. So if you look at the earthquake load, the red curve here, it represents the response of the structure. Right? So this is the positive response, this is the negative response, and this is the time along the x-axis. Okay. So you can see here that the structure responds with 0 mean. Of course, the cyclic response is there, but then the mean is 0. So it responds about this 0 line, about this mean line. But during the wind loading, the structure again responds in an oscillatory cyclic manner, but then the mean is not 0. Okay, it is a non-zero mean. So this is primary difference, and you can see the response of the structure, which is much less compared to this response during the earthquake. Okay, so this is a primary difference, that it is zero mean versus non-zero mean. Now, it is not only about the 0 mean, but it also about, I mean, a lot of structural response depends on where it is located in the same city, but what type of soil is there. So I will give you one example here. There was an earthquake in 1985 in Mexico City. Okay, so this story is very interesting, that we had at that time two types of, two locations where the accelerometers were installed. So one is this SCT site, which is this soft soil of the lake zone. So this was a historic lake which was filled up, and then structures were constructed over this lake. So this was a alluvium filled up soil site. And there's another site which was rocky, and this site is known as Unam, and this was the site where we had 3 to 5 meters of basalt rock, right, underlain by the softer soil. So here is a softer soil, but then top 3 to 5 meter rock was there. Okay, and so structures were constructed above this, and in this case the structures were constructed over the filled up soil. So as you know, what is the resonance? The resonance is basically when the frequency matches. Okay, frequency of two things match, so we have the resonance. So here what happened, that the ground motions and the structural frequencies, they matched. But before coming to that, let me tell you what is the important point here. Why I am discussing this. So the response of the structure is basically the structure will respond to two different types of loading during earthquakes and winds. So during earthquakes, we have the acceleration at the base that we have already observed, but during the wind, we have the lateral pressure on this building. Okay, and that's why we have the lateral displacement. But earthquakes, we have ground deformation, we have ground acceleration, because of which the base of the structure moves, and therefore the accelerations are transferred to the top at the upper levels of the building. But here, the ground remains stationary, and we have lateral forces of varying magnitudes along the height of the building. Okay, so this earthquake forces, we call them displacement loading, and wind forces, we call them force loading. Okay, it is very interesting. What is the difference? So I think this we already discussed yesterday, that why earthquake loads are more important, because we have tension and compression bending on both the faces in case of earthquakes. I will not repeat it here. So the important point here is, because the earthquake shaking reverses, we have to provide the steel on both the faces. And another important point, why do we have the damages more near the ends of the members? So that we discussed yesterday. Now coming back to again what happened in the Mexico earthquake. Now, and also relating it with the type of force, whether it is a force control loading or it is a displacement control loading. Like I said, earthquakes are displacement control loads. Okay. So before we actually go into the Mexico earthquake story, let us see what are the uncertainties in the ground motion. So first uncertainty is when and where is the next earthquake, right? That we have already discussed. On which fault? We don't know, we cannot predict, because they all keep moving in different manner. Of what magnitude? So what is the size of the earthquake? Nature of the ground shaking near source, right? So this is the source. What type of ground shaking is here? Is it subduction zone, or it's some different type of plate tectonics happening there? Effect of travel path on shaking at a distance. So what type of soil is there when these waves travel, when these energy waves travel from focus to these structures? What type of soil is there? So is it actually changing the type of the waves? So the travel path is actually very important. So when these waves travel, they attenuate when they reach the structures, right? And the attenuation depends on the soil profile, also on the frequency of these waves. Okay, so when the frequency of the waves and the frequency of the soil, it matches, then you have very high, very vigorous resonance movement. Effect of local geology, topography and soil profile, like I already discussed. So these are the uncertainties. So now you can see there are so many questions, there are so many uncertain things when we talk of these earthquakes. Now considering these, I'll come back to that Mexico City earthquake story. Okay, so we now know that the structural response, it depends on the input motion, right? And it also depends on the structural properties. So if I show you this figure here, where on the y-axis I have some acceleration. This is called pseudospectral acceleration, PSA. So this is the acceleration of the structure. And on x-axis I have the natural period of the structure, right? So this is not the time during the earthquake. So if you remember the ground motion shaking recorded by accelerometer, this is not that t, but this is the natural period of the structure. And this is the pseudospectral acceleration of the structure. So you can see, if you remember, what was the unum site? The Unum site was the rocky strata. Okay, and the SCT site was the filled up soil where the structures were constructed above this filled up lake. Right. So the instruments were installed at both the locations, and when this curve was plotted, this PSA versus T, which is actually known as response spectrum, the response of the structure, and spectrum means how it changes with time period, right? So this is called the response spectrum. So when we plot this response spectrum for these two types of structures, for these two types of, considering these two different soils, considering 5% damping, you can see the difference, right? Now, if you have structures whose natural period of vibration is in this zone, so maybe between 1.7 seconds to about 3 seconds. So this is the region where most of the high-rise structures are located. Okay, there is a very simple way, very approximate way and simple way to calculate the natural period of vibration of buildings. That approximate way is, if the number of stories in a building is 10, the natural period of vibration will be 1 second. So it is 0.1 times the number of story, right? So just by looking at a building, very approximately you can guess like what will be the natural period of vibration. So 1-story building will have a natural period of vibration of 0.1 second only. So it will vibrate very quickly. But then high-rise structures, they will vibrate slowly. So they have higher natural period of vibration. So these are the structures you can say here about maybe high-rise structures from 15, 16 stories to about 30 stories, because it is a developed city, Mexico City. So you have these structures. Mostly these structures were there, and you can see that those structures which were located on Unum site, they were required, they were, the demand that the earthquake put was very less. So they were subjected to only this much peaks, the pseudospectral acceleration. But the structure, same structure, similar kind of structures which were located on this alluvial soil which was filled up, the demand was very high. You can see here the demand was actually more than 5 times, right? So you can imagine the same structure, same city, but then depending on that soil profile, the response can be very different. Now, of course, during that earthquake, large number of structures located in that SCT collapsed, but the structures located on Unum did not collapse. So, and you may read newspapers, you may read the earthquake, post-earthquake reconnaissance reports, and you will find many such stories that 2 buildings, similar buildings, located in a region, one collapsed and the adjoining building did not collapse, right? So, one reason out of many other reasons, maybe the soil profile may be slightly different. Some filled up soil may be there, okay? But that can be only one reason. There are many other reasons. Now, let us look at what are the uncertainties in the structural properties. So we have looked at the uncertainties in the ground motion. Okay. Now, structural properties, we are very much advanced. We have such a nice facilities, laboratory across the country, in the whole world. We have such nice instruments. But then still, the estimation of natural period of vibration of the structure is very difficult. It's not actually possible to find out what is the actual natural period of vibration of a structure because of various issues, because of the connectivity between different elements, because of the interaction between different elements, non-structural elements, then the different masses sitting on different locations in slabs. So it is very difficult to calculate natural period. There's a high amount of uncertainty in the stiffness estimation. So just to give you one example, if I show you the stress strain curve for, let us say, concrete. So this will be the generalized stress strain curve for concrete. And if I want to find out what is the modulus of elasticity for this concrete, so basically I want to know what is the stiffness. How will you know? The basic assumption here is the point up to which the material behaves elastically. So we can take slope of that. But then in real life, when you test these cubes, concrete cubes in lab, you will never get the linear response. It is always non-linear from the beginning, right? So in that case, how will you get the stiffness, or how will you get the modulus of elasticity? So there are various methods people have come up with. So these methods are shown here. The method is, one method is by doing this initial tangent modulus. Another method is calculating the tangent modulus at another point. Third method is calculating the slope of the secant line, calculating the chord modulus. There are various methods, right? So then, since there is no standardization, people will report different types of stiffness without even worrying about that my other colleague in some other country, he may be actually reporting chord modulus, but I am reporting the tangent modulus, right? So that is why if you look at IS 456, the Indian code, it simply says that you forget about all these things. You simply calculate the modulus of elasticity for concrete as 5000 under root of FCK. Okay, so FCK is the characteristic cube strength of concrete at 28 days. So you test hundreds of cubes, find out what is FCK, and take under root of that, multiply it with 5000. That will give you the modulus of elasticity of concrete. Now, do you think that there is no error here? The error is huge, and you will be surprised to know that in majority of the cases, the errors are more than 50-60%. But then we are still comfortable because we know that in all regions of India, across the country, everybody is using that same equation, right? So if I say that this is M25 grade concrete, and the entire country, people will say that the modulus of elasticity is 25,000 MPa. So that gives us some confidence. Now the uncertainty issue can be handled separately by having some factor of safety. That is what codes do. I'll come to another common material, which is masonry. So if I plot here the modulus of elasticity of masonry versus compressive strength of masonry in different parts of the world, so you can find such a large distribution. Look at the scatter here. This is such a big scatter, and if I try to if I try to find out how much is the variation in the modulus of elasticity of masonry, so it varies from 210 times Fm prime. So this Fm prime is basically the compressive strength. So like we calculate modulus of elasticity of concrete as 5000 root FCK. Similarly, we calculate the modulus of elasticity of clay brick masonry using a very simple equation, some factor multiplied by the compressive strength. So that factor here is 210 to 1670. Now you just imagine there is a difference of more than 8 to 10 times, right? So unless the code gives us some number, it is actually difficult to do some standardization. So in our code, now recent code, it says that you consider the modulus of elasticity of masonry as 550 times Fm prime. So that is standardized. Okay, so Fm prime will be different for different bricks, for different masonry, depending on the type of brick, depending on the type of mortar, but then the factor remains the same, 550. So that is uncertainty in only stiffness. Now you can imagine the uncertainty that will be there in the damping calculations, which are difficult to actually estimate. The uncertainties related to soil foundation interaction, we cannot see what is there below, right? So how will we model it? The post-yield behavior, we say that the properties of steel are very well standardized, but then it depends on who the manufacturer is. So post-yield behavior of the steel, it actually affects the post-yield behavior of the entire building, entire members. So these are the uncertainties. Now considering all these, we say that there are so many uncertainties related to the ground motion, there are so many uncertainties related to the structures, then uncertainties related to the ground itself. Still we say that you expect damage, but there should not be any collapse. Now that is achieved if you can actually regulate the amount of damage, the level of damage in these structures. Now, how do we do this? So there are many analysis methods available. starting from linear static analysis, where we have this equivalent static analysis given in the code, linear dynamic analysis, response spectrum analysis given in the code, time history analysis, which is difficult than the linear static analysis, but then simpler than these methods. So nonlinear static analysis, which is also commonly known as pushover analysis. So where we consider the material nonlinearity as well as the geometric nonlinearity. And then finally the nonlinear dynamic analysis, so which is basically the time history analysis. Now, those of you who are doing some research on seismic analysis and design, they will be quicker to understand that when you go from top to bottom here in these methods, the time required, the effort required, and the difficulty level increases drastically, right? So if you want to carry out a nonlinear dynamic analysis, the amount of data that you need to feed into the system is huge compared to simple linear static analysis or even linear dynamic analysis. Here, what you only need from the material side is only modulus of elasticity. Okay, not even strength, right? Because it is linear static analysis. In linear dynamic analysis, you have to actually, specify the design response spectrum. That's all. But otherwise, you don't need anything. In time history analysis, you need the ground motion. But still, we are saying that the response remains linear. But then, when you want to model the nonlinearity, you have to actually define the material nonlinearity. You have to specify that these are the locations where nonlinearity will be there, and these are the properties of that nonlinear behavior. Nonlinear dynamic analysis, you again require a lot of properties, many properties which are not required otherwise. Okay, so it is extremely difficult to do nonlinear dynamic analysis. But then the problem is, if you use any software, it will do some analysis. You model something and you say that you carry out this analysis, it will give you some results. Now, unless you understand those results, it is very difficult to actually have confidence on those results. So whenever you have to do some seismic analysis, always go with the most simplistic linear static analysis first. Try to understand how the structure behaves. Then you move on to linear dynamic and slowly to nonlinear static, and finally nonlinear dynamic. Don't do nonlinear dynamic analysis directly without even doing the linear dynamic analysis. Otherwise, you will not be able to understand how is the structure behave. Now, I'll again come back to the implications. Okay, so nonlinear dynamic analysis is desirable. Like I said, it is very complex, it is very time consuming, it is really expensive because you need good computers, servers, workstations to carry out these nonlinear dynamic analysis of bigger structures. So, for example, I have a expensive workstation, and when my students they carry out nonlinear dynamic analysis of even a small single frame of a building, single story. Sometimes it takes more than a day, or more than 2 days, 3 days to complete the analysis. There are numerous uncertainties in input motion. So people will ask, when you carry out the time history analysis, which ground motion are you using? Because there are thousands of ground motion. For which ground motion you will carry out the analysis? So these are the problems. And we require various parameters that are not easy to actually determine in these types of analysis. Linear static analysis, of course, the amount of data required in input is much less. So for most purposes, people actually consider these method of analysis adequate. But then we have to somehow incorporate the inelastic dynamic behavior into this linear static or linear dynamic analysis. So we have to, as an engineer, the job is to actually use a simple design approach to a complex problem, but without ignoring the complexities of the problem, right? So that is the whole idea. Now let us discuss what is force controlled versus displacement controlled. If you remember, we said that the earthquake loads are displacement controlled, but the wind loads are force controlled. So if you have a simple RC beam, like here, fixed at one end, and you're applying this load P. So you're keeping on increasing the magnitude of this load, and you're plotting that magnitude of load here with the displacement delta that this beam is undergoing. Okay, so this is equivalent to the earthquake load, gravity load. Now failure will occur if the imposed load, this P, is more than the yield force. Okay, now let us see why failure will occur. So if you keep on increasing this P, initially you will get lesser displacement for less P. So for higher P, displacement will increase. You keep on doing this, you will reach a level where even if you increase that force, the displacement will not increase, right? Or I will say it in a different way. You cannot increase the force beyond a level because it cannot sustain, right? So if it reaches this level beyond which it cannot take any load, how will you increase the load? So the point is, you cannot plot this curve completely. You can only plot up to which force is increasing. But then displacement may increase further, which you can't do it here. So this is the test that we carry out to know the FCK value. So the tubes are tested in this manner. You go to CTM, the compression testing machines, put the tube there, and you start loading the tubes. You will find that after a particular level, the machine will stop operating because the load is not increasing further. So this is the problem with the force control systems. Okay, because you cannot increase load beyond a point where the force is started reducing. Okay, now if you compare this with the displacement control system, so now I keep on increasing the displacement and measuring the load here. So I'm applying the displacement and measuring how much load is required for this displacement. Again, I increase displacement, measure the load, keep on going the displacement. Irrespective of the level of P, I can always go on increasing the displacement. Right? So this is much better then. So if the force starts reducing here, I can still keep on increasing the displacement. So this is much better compared to the force control systems. So here I cannot measure the force beyond a level, but then I can always keep on measuring the force as long as the displacement keep on increasing. Okay, so here that is why I said that when the imposed load is more than the yield force, you have the failure. But here you will not have failure even if the imposed load is greater than the yield displacement. Why? Because we are putting the ductility into the picture now. We are displacing the structure. We are not forcing the structure. Right? So that is the primary difference. In wind loads, in gravity loads, you force the structure. But in earthquake loads, you displace the structures. Right? And that is why you have some control over the response of the structure. Now, this is the earthquake force. Like I said, the inertial force is mass times acceleration. And the acceleration is acting at the base, obviously. So when the base moves, the top of the structure remains at the same location at that instant, and therefore you have that inertial force, right? So after an instant, this will try to move, but then the force will reverse. So that is what happens during the earthquake. Now this force, which is at the base of the structure, it actually requires to be transferred to different levels. But then when we say that force is mass times acceleration, so acceleration is acting at the base, but then the mass is not at the base. The mass is distributed over the building. Where is the mass? Majority of the mass is located at the slab levels, right? If it is a multi-story building, wherever there is a slab, you will have larger distribution of mass there. Obviously, you will have walls and columns and shear walls and beams at different locations. So this mass is also there, but then still the whole mass of this wall is actually transferred to the beams, and that beam transfers the mass to the next level. So wherever you have slab, you have mass accumulation. You have majority of the mass, and so the acceleration when it acts, the forces are also generated at these levels, wherever you have masses, right? So higher mass at a level means higher acceleration, higher inertial force at that level with same acceleration. Okay, so when these forces are acting at this level where there is a mass, these forces are transferred to the members which transfer this force to the foundation. So that is uh, the manner in which their forces are transferred to different elements and finally to the ground. Now, ground vibrations, they are random in magnitude, and like I said yesterday also, that even if you have a perfectly symmetric structure, your ground motion direction may not be symmetric, it may be random. So there is always a case of unsymmetry. So there can be n number of directions in which seismic waves can travel: vertical, horizontal, inclined. But then we cannot design, there is no need to actually design for random directions and random magnitude. So therefore we assume that there are two horizontal shaking directions and one vertical shaking direction. So these are the principal directions of a building, right? So if this is a building, irrespective of the actual direction of the ground motion, we design this building for the plan irregularities. So basically it has included all vertical as well as plan. If the structure is rested on soft soil, if the structure is a bridge, or the structure has a long span, and if the structure has large overhangs, horizontal overhangs, for example, large balconies in residential apartments. So if any of these criteria is satisfied, then you have to carry out the consider the vertical earthquake effects in the design. What is the problem with the long span or a bridge? Why do we need to consider the vertical shaking? Because if you imagine a building as a vertical cantilever, right? Then we consider the horizontal ground motion and how this building is vibrating. So if the building is vertical cantilever, the ground vibrates at the base. Now similarly, if you have long span structures which are horizontal in nature, then you have to also worry about this vertical shaking. Okay, so that is the reason. So when we have both horizontal and vertical seismic forces, then the load combinations for the three directional earthquake ground shaking should be considered. Right? So you have to consider some combinations. Finally, you have to design the same structure. So if there is a column, you have to design that column for X direction shaking, for Y direction shaking, and for Z direction shaking. You cannot say that this reinforcement is only for X direction, this reinforcement is only for Y direction. It has to be a combined response. So somehow you have to combine these three directional earthquake ground shaking. Okay, now let us see what is the response spectrum in slightly more detail. We'll have additional discussion on this later, but this is just an introduction. So what is the response spectrum? It's basically the response of a linear elastic single degree of freedom system. Okay, now it will have its own natural frequency, the single degree of freedom system, so its own natural period and damping. So here is the single degree of freedom system where you have one mass located at this level, and these columns, they provide the lateral stiffness, and this single degree of freedom system is fixed at the base on the foundation. And like you already know that the acceleration now acts at the bottom. Okay, so when the acceleration acts at the bottom, you have the inertial force at this slab level, right? Because the mass is located here, so force times the mass times acceleration will give you this inertial force. Okay, now response of the single degree of freedom system, it depends on this acceleration, the input motion. It depends on its natural characteristics, so the natural period or the frequency. It also depends on the damping. So if you remember the response spectrum that I showed, if you plot that acceleration of this mass, single degree of freedom system, so this acceleration of the mass, if you plot here with respect to the natural period of the structure, then you get certain response, right? And for different damping, you will have different responses. So obviously, if the damping is less, the response will be more. If you go on increasing the damping, for example, this curve here is for 20% damping. Okay, and 20% damping for the structure. But all these response spectra, they are developed for L centro ground motion. Okay, so it's a normalized pseudo acceleration or ratio coefficient that we use here. So it's basically a plot of maximum response of that single degree of freedom system, right? It is a maximum response. Now, where is the single degree of freedom system in this response spectrum? It will be any one point on the natural period. So, natural period of this single degree of freedom system is, let us say, 0.2 seconds. So, here is the 0.2 second, right? This is 0.25, so 0.2 is somewhere here. So, any one point on this response spectrum will correspond to this structure here. Okay. So, if the structure has 20% damping, this will be the acceleration, pseudo-spectral acceleration. If the structure has 0% damping, the acceleration will be here. Okay. Now you can ask, what are these remaining points then? The curve is continuous. If this structure corresponds to only one point here, what are the other points? So other points are basically, we keep on changing the mass, we keep on changing the stiffness. If we do that, the natural period will change, because what is the natural period equation? It is basically 2 pi under root m by k. So single degree of freedom system. So when you change mass or when you change stiffness, you change the properties. Okay. So that is how we generate this response vector. And response can be force, it can be displacement, it can be acceleration. So design spectrum is different than the response spectrum. So here is the design spectrum given in the code. So it's a design specification, right? So if you compare these two curves, you will realize that the previous curve was not as regular, not as gradual as this, because this is an average curve. This is developed based on thousands of ground motions. Okay, but the important point here is you can see that for softer soil, so this is type 3 softer soil, this is type 2 medium soil, and this dark line here is a rocky soil. So obviously for a same structure of natural period 1.0, if it is located on soft soil, the response will be more, right? If it is located on a rocky strata, the response will be less, acceleration response. Okay, so it is required to be designed for less acceleration, right? So we'll discuss more in the, there's a lecture on response spectrum method that will discuss more. Fundamental natural period, of course, we have, the code has given us several equations, because like I already said, it is very difficult to find out the natural period of vibration, but our code has given these equations for bare moment resisting frames, for buildings with RC structural walls, and all other buildings. So using these equations, we can get the natural period of vibration. The buildings with masonry infills, they fall under this category. Okay, so this formula does not change. It is same as the previous version. Now, there are 4 virtues of earthquake resistant constructions. So strength, stiffness, ductility. Finally, the configuration. So these are the 4 virtues. So the strength, stiffness, ductility, it comes from structures, right? From structural engineers, from structural codes. But the configuration, it is coming from the architects. So when you mix them, there is always a fight. So this cartoon I already showed you yesterday, that architects, they want certain configuration, but it may not be suitable for earthquake resistance. So we have to find a common way ahead. Now let us see how the strength and ductility are related. So if I have a simple structure and I'm applying lateral force, I'm measuring delta and plotting this. Okay, so this is the lateral load and this is the displacement. So if I assume the linear response, this is how the displacement versus force look like. If I assume the non-linear response, we have 2 possibilities. The first possibility is, if the structure is ductile, then it will not fail suddenly, right? But if the structure is ductile, if the structure is non-ductile, if it is brittle like concrete, it will fail suddenly. Okay, So that is how, if you remember the stress strain curve for concrete versus steel, for concrete you will get such a curve, for steel you get such long curves, right, which have high ductility. Now it's up to us actually to properly decide which is the design force. So if this is the maximum elastic force, this is the maximum inelastic force, where do we have the design force? That is the whole challenge. So this challenge is actually, simplified in the design code by the use of this factor that is called response reduction factor. Okay, so let us see what is this factor that takes into account the ductility. So again, the same figure here, but I'm removing the brittle response figure. So this is the linear elastic response. How do the structure respond like this? See, linear elastic response is just an assumption, but in reality, the structures always are subjected to some damage, some cracking, right? So some non-linearity. So because of ductility, the structural response reduces from here to here, let us say. So this corresponds to maximum load capacity. Okay. Now there are certain other reasons that we can further reduce this load to this level, which is the design force. Right. Now what are these reasons? One is of course ductility. You understand that because of ductility, the structure will not remain linear, but it will be subjected to the non-linearity. And if the structure is ductile, you can actually sustain the lateral displacement without failure. Okay. Now this is the level of first yield. So from here you will have a different response, right? Elastic versus non-elastic. Now from this level, beyond that level controlled by ductility, redundancy play a role. Now what is redundancy? Let us say in a building, when you design, you need 36 columns. But then for functional requirements, you have to provide far more number of columns and beams. So those are the redundant members. And in case the main member fails due to certain reason, this redundant member takes that load, right? So redundancy always helps. Then you have overstrength. Overstrength means if you have, let us say, tested concrete cubes in lab, you design the structures for FCK, right? But FCK is not the actual strength of the material, strength of concrete. What is the actual strength? It is a target strength, and it is much more than this FCK. Similarly, when you test a steel reinforcing bar in lab, it is not 415 MPa, right? For Fe 415, the strength is not 415, but it is much larger than that. So we have certain overstrength of the material. So because of all these issues, we have certain safety margin, and we can reduce this elastic response to an inelastic response, and we can achieve a level of design force. Now, we also have certain criteria considering the stiffness deterioration and degradation. So, like you know that the earthquake is not a monotonic load; it is a cyclic load. So, when the structures are subjected to the cyclic loads, you always have strength deterioration. So, because of the cyclic loading, the strength will reduce, and also the stiffness will reduce. It will go on reducing because of the cyclic load. So what will happen to the cyclic energy dissipation then? So if I show you these curves, if I test this structure in laboratory and I slowly keep on applying this load, cyclic loads to and fro, I can plot this curve here like this. And those of you who have done some tests in laboratory, they know that these curves are known as hysteresis loops. So anybody will tell you that these hysteresis loops are poor, these hysteresis loops are much better. And if you want to find out what is the area under this curve, under each of these curves, so this area will be much larger than this. So obviously the energy dissipation under this, in case of this structure, will be much better than energy dissipation here. And you know that the seismic waves, they are energy, So they have to be dissipated. So the structure that can dissipate larger energy, that will behave in a much better way. Okay, so these structures are much better. So for that, you see here, the structure is not as ductile as this. The structure is not behaving in a much better hysteretic manner, this structure, compared to this. So obviously this structure will behave in a much better way during an earthquake. So this is how we define the ductility. So if you test this structure in lab and you plot the response, the load versus displacement, this is the idealized response, because it is difficult actually to find out where is the yield displacement. So we idealize the response. We say that we assume that here is approximately the yield displacement and the yield force, and this is the displacement after which the strength started degrading. So this is, let us say, delta max. So ductility is defined as the ratio of this maximum displacement to yield displacement. Okay. So then for the overall structural ductility, we have the base shear versus roof displacement. From that you can even calculate the story ductility from the story shear versus story drift. The member ductility, displacement or rotation, you can calculate from transverse force versus displacement rotation to that member. And you can also calculate the section ductility, the curvature ductility from moment versus curvature. So all these terms are important in seismic design, because starting from the section design, you have to go for structural design. So then this linear elastic system, we have actually converted into an elastoplastic system. So this response of a single degree of freedom system to a given ground motion, we can convert from here to here, considering all of that, right? So ductility, where we have all those parameters. So here is the ductility reduction factor. So from elastic response, we go to the ductile response, right? So when we go from elastic to ductile, you now know that we reduce the force. The smaller and smaller force will have to be designed, considered for design, if our system is more and more ductile, right? But then it should not fail. So this level, for example, it fails here. This structure, it will fail here, but we don't want that. We are okay with reduction in the design forces, but we want higher and higher ductility. But it also has a upper limit. So this, we can ensure the ductility, and we can design the structure to yield at a reduced force then. Okay, so here this is the yielding force, here this is the yielding force. For this structure, this is the yielding force, right? We can do that. In order to do that, we require this ductility reduction factor, R mu. So this is basically F max divided by Fy, at which level you want to actually reduce it to. Okay. So of course it's a function of ductility and the natural period of vibration. Now the overstrength factor, like I said, it is basically the ratio of the yield force and the design force. So this is the design force and this is the yield force. So from here to this design force, we reduce on the basis of this overstrength factor. So the contribution of this overstrength is basically the load factor on the seismic load, the load factor on the gravity load, the material safety factors that some of you already know, 1.15 for steel and 1.5 for concrete, member sizes reinforcement that is more than required, the spatial ductile detailing, it also affects the overstrength, contribution to overstrength, and then the redundancy, the strain hardening in steel, even in concrete, the higher material strength under the cyclic loads, and the strength contribution of non-structural members. So all of these, and there are certain other parameters depending on buildings. We can have additional parameters that affect this, that contribute to the overstrength. Now finally, considering all this, we can now define the response reduction factor. So this response reduction factor consists of the ductility reduction factor and the overstrength omega. So R mu omega. So the response reduction factor is R mu omega, and we generally assume that this redundancy is included in the overstrength. Okay, like I already discussed. So this design force we can now reduce from the maximum elastic force by dividing it by R. Okay, so this R can be as high as 12 for special ductile. So now you can imagine that if you want to actually design a structure for earthquake, for safety under earthquake loads, then you can reduce the elastic design force by 12 times. But for doing that, now you know that the structure has to be ductile, there has to be good overstrength, there has to be good redundancy, and many other factors. Right? So this is what we have done. This is the elastic response, and using this R value, we have reduced this elastic force to the design force, which is much less, maybe 10 to 12 times less. Okay. So like I said, this is a poor structure, this is a medium structure, and this is a good structure. So we have to actually design these structures if you actually want to control the damage. Otherwise, we cannot control damage using these types of structures. So that is why we say that we have to rely on the post-yield ductile response. Right? Only then we will be able to achieve the objectives of seismic design philosophy. So the lateral stiffness and contribution, this is one important aspect here, that if you have, let us say, low lateral stiffness, so there are certain problems. So what do you mean by low lateral stiffness? So if you remember, the natural period is 2 pi m down m by k. So when k is very less, the natural period is very high, right? So that means the structure will vibrate very gradually, very slowly. But since the stiffness is less, you have large deformations, right? So if you have large deformations, large strain, so you have more damage in the inelastic response, right? So in that case, the P delta effect will be significant. We'll discuss more about this later in the nonlinear analysis, last lecture. What will happen to the non-structural elements, right? If you have higher deformations, all these pipeline fittings, electrical fittings, all these temporary structures, or the fall ceilings, they will be subjected to huge displacements, right? Large deformation, and you will have discomfort. So all these non-structural failures will take place. So therefore, we cannot have very low stiffness, right? We cannot have very high ductility, just to reduce the amount of displacement. So even though the design force is low for high natural period structures, the stiffer structures are preferred sometimes because of this. So if you have this structure compared to this structure, so this has very high natural period, so obviously the stiffness is less here. But if I consider the displacement spectra, the displacement is much higher because of lower stiffness. So this is not desirable. For this structure, even though the acceleration response is much more, the design force is more, but then the displacement is much less. So sometimes it is actually easier to design the structure for higher force but lesser displacement. That is what is meant here. So the lateral stiffness and configurations are basically related. So it depends on the geometry, size, shape, depends on the location and size of structural element under consideration, and the location of size of non-structural elements. So for example, here if the forces are to be transferred from this level to bottom, you can see it has to change direction so many times, right? So therefore, wherever it changes the direction, you have damage, right? And if you have infills, of course, the damage will be of different kind. Type of structure, type of configuration, convex versus concave, it really plays a role here. So this is a very interesting type of irregularity. If this is a structure in plan, and if you have if you consider any 2 points on this structure, you try to join these 2 points. If the line joining these 2 points fall outside the structure, then it calls it is a irregular structure, right? Now, which type of irregularity is this? You go and check the IS 1893. It will tell you what type of irregularity is this. But if you consider the convex structure, there is no line here which will fall outside. If you consider any 2 points on the structure, the line will always remain inside the structure. So this is a better structure. This is a poorer structure. Now, what is the problem here? What is due to this irregularity? There will be high stress concentration in this region, so there will be more damage here. But this is a good structure. So then, simple direct load transfer path, it always gives you better performance. Regular configuration is always preferred because even distribution of mass and stiffness in plan as well as along the height, that is desirable. In buildings with irregular configuration, ductility demand, it gets concentrated in a few stories. If you remember yesterday's presentation, the open ground story buildings, the ductility demand was maximum in the ground floor. So that is the problem. So simple code expressions, they are not valid. We have to actually develop guidelines for that. So whole section of IS 1893 is actually devoted to this, and I will recommend you to go to this section in IS 1893 that discusses the configuration, seismic configuration issues. So finally, we have to satisfy the design objectives of the seismic design philosophy. The column should always be stronger than the beams. Damage should be regulated, and now you know how can you regulate the damage, right? It is possible. There's a very interesting philosophy that is called capacity design concept. So that will be covered by my colleague Professor Kaustubh Das Gupta, I think tomorrow. So that is actually very essential if you want to regulate the damage. So damage should occur in identified members only. So we have to identify certain members only where we can allow the damage. For example, we cannot allow damage in the foundations because it's very difficult to retrofit them. Design should be such that the damaged members can be quickly retrofitted, right? The capacity should always be more than demand. So what is the capacity? So all the reinforcement, all the members, walls, everything, they contribute to capacity. And what is the demand? Demand is the earthquake load, right? So we always know that this capacity should always be more than demand. So this is all from my side. I would like to thank National Information Center for Earthquake Engineering and Professor CVR Murthy of IIT Madras because I have borrowed some of the material from them. And these are some of the resource books that you can actually get from libraries. Some of them are available on internet. For example, the earthquake tips, they are freely available on this NICE website. These are very interesting tips, and you will find several figures that I've used here in these earthquake tips. And these are some of the very good books available. Some are Indian author books, some are foreign author books. But if you have some of these books and materials, you will be comfortable in the seismic design. So thank you very much. If you have any questions, I'll be happy to address, and I will stop sharing my presentation. Hmm. Yes. Yes. And the good curve will always, yeah, I mean, see, the structures are not only concrete structures. Okay, the structure is reinforced concrete. So the way we design it, the way we provide ductility, the way we detail the reinforcement, it actually controls how better hysteretic response we can get. Both the responses that I showed are for reinforced concrete only, right? So one for poorly designed and poorly detailed, and one for design in detail in a much better way. And it is possible even in concrete structures. Yes, yes. See, no, no, it is perfectly related to this. In IS 1893 2016 version, we have included this property modifier. Before that, it was not there in the Indian code, but it was there in many other codes. Now, it is very important step towards seismic design, because what happens when you construct a structure, especially a reinforced concrete structure, like I said, models of elasticity is 5000 root FCK. But as soon as I construct the structure, some loads are acting on the structure. These loads may be wind loads, these loads may be gravity loads, maybe due to some vibrations, heavy movement of trucks. So always there is some kind of loading. Because of that, there is always some formation of micro cracks in these structures. So if you test these structures, you will never get this 5000 root FCK. It is always less. Now, how much less? You will be surprised to know that if you test these structures in laboratory, the stiffness is reduced to about 50% even before any earthquake has occurred. Okay, in case of columns. In case of beams, it can be even more. So that is why the IS 1893 recent version, it has these stiffness modifiers. And it is very important. You have to consider lesser amount of modulus of elasticity. Yes. See, this 12 is the real number. If you test in laboratory, you can even get 15 or 20, right? But then we cannot do it in design because there are several safety factors. So, because one person can actually do it in a very nice manner, he or she will provide nice ductile detailing, big size columns, strong column, weak beam, he'll do everything. But then same structure, someone else is designing, these conditions may not be satisfied. So then you must have some safety factors. So even if the response reduction factor can be as high as 12 or even more, the code will never allow you to do that, to use that. Okay, so therefore there is a restriction on the maximum number of R values. See, this is a very tricky thing again. What is structure? You have to define the structure because natural period you are calculating for a structure. So if you think that the headroom or any other structure that is at the top of structure, it contributes to mass and stiffness, then you have to consider up to that level. If you think that this is not contributing, then you can actually remove that much amount of height. But then if you look at 2016 version of the code, there are many more details now given in the code. It tells you different types of structures, different stepped structures, from where you can actually use the what is the bottom level of the structure and what is the top level of the structure. But still, the code cannot give you all the possibilities, right? It can only suggest some possibilities. So for different possibilities which are not there in the code, we have to use engineering judgment. And one engineering judgment that I generally use is this: that is this portion of the structure contributing to stiffness and strength? Then I will include it. If it is not, then I will not. Yes, yes. See, if code gives you an equation in which stiffness is required, how will you calculate it? Right? It is not easy to calculate stiffness because I showed you, even in case of simple concrete cubes, it's very difficult. So then what code has done, it has actually considered large number of tests and doing some analysis of the data, it has come up with these equations in which the stiffness is inside the height, the stiffness is inside the width. So all this contribution of stiffness is considered in height and width of the structure. It is already incorporated but not there as a stiffness term. It is simplified way. Uh, See, the code actually gives you the n values, right? Using which you can differentiate what type of soil is it. Okay, so there is a table given in the code. So you can identify using those numbers, those n numbers, which is the type of soil. Now, if you are on a site and you want to know what type of soil is it, then you need to test this soil in laboratory. Okay, find out different properties, and then even, I mean, you have to conduct the SPT test also, the plate load test, different types of tests you have to carry out, and then you have to come up with the geotechnical investigation. Based on that, you have to come up with the type of soil. How can you increase means, I'm not understood. Maybe he wants to know how do we improve how do we reduce the design force by changing R. See, let us say you have a, reinforced concrete frame building in which the ductile detailing is not provided. Okay, so for such structures, we don't expect a very good ductile response, right? It will fail suddenly. Now, for such structures, we cannot reduce the design seismic force because we know it can fail suddenly. So for them, the design force will be higher. Now, if we can provide some ductility, if the material properties are better, the the reinforcement detailing in the sections is much better, then we expect higher ductility in the system. And when we expect them, we can use higher value of R. So if you use the IS 1893, it says that are these frames special ductile detailed frame, or these are normal frames. So for frames with special ductile detailing, which actually allows the ductile response, which will not fail suddenly, for them the R value is higher. So if you want to reduce the design forces, you have to increase R, and you can increase R by providing higher ductility to the section. Okay, by having good or better seismic detailing. Yes, why not? Yesterday also someone asked, can I design flat slab building for circular column? So, I mean, if you ask me as a structural engineer, why not? We can design anything. So, confined masonry is, of course, we are now preferring over even reinforced concrete with masonry infill because of certain reasons. One important reason is we are not able to design these reinforced concrete buildings properly because of these issues. Like, there's so many factors: response reduction factor. Then you have to be careful about ductility. You have to be careful about the configurations. Many factors. In semi-urban areas, in rural areas, it is difficult to find engineers who can do this. So therefore, we are proposing that in such areas, we leave the reinforced concrete buildings, but then we come up with the confined masonry buildings in which not much engineering judgment is required. It is designed on the basis of some thumb rules. No ductility is required there. So no response reduction factor. Perfectly possible. This is a very good question. See, how much vertical force will act, that is specified in the code, right? So two-thirds of that, the horizontal design force, or half of the horizontal design force, some values are there. But then, how do we distribute this vertical design force to different members? Now, you have to actually look for those members, those vulnerable members in the building, which are to be designed for this vertical force. So not the entire building is required to be designed, right? Some members which are uh, which are responding to this vertical shaking. Only those members are vulnerable, right? So you have to identify those, and when you do the analysis, you apply the vertical force and then you see how much is the design force there. For example, large overhang. Like I said, if you have this overhang and you apply horizontal shaking, it may not be that it may not be that influential in this case. But if you apply the vertical shaking, then this member will vibrate more. So you have to identify those members and then design from considering the design forces from proper analysis. No, we can apply vertical also. There is a very big shake table at SERC Chennai, Structural Engineering Research Center. So they can test, I think, a full three-story building in six directions. So they can apply three horizontal motions. Sorry, they can apply this X and Y direction motion. They can apply vertical motion. They can also apply the rotation at the base. So that is perfectly possible. We have these shake tables. See, for shear wall buildings, there is a formula given in the code. You have to use that formula for design purposes. But then if you are doing some research and if you want to come up with a different design, if you want to come up with a different formula, then of course you can try different things. But if you are designing, you have to use this formula only. Okay. See, it depends on what type of analysis you are doing. Let us say you are doing the first analysis. In my presentation, if you remember, the first analysis, the simplest analysis was linear static analysis. Right? It is the seismic coefficient method given in the code. Now, in that method, you have to calculate the natural period manually, right? Using these equations given in the code. Okay, so how do we do this? You know the structure, you find out the natural period, you go back to the response spectrum, find out the value of design base shear, and then you apply this design base shear and do the analysis, right? This is the method. But if you are using the next method, that is the response spectrum method of analysis, so the only difference between these two methods is now when you model the structure, you also give the response spectrum as input to this software. So the structure will calculate the natural period of vibration based on the properties of the structure, the mass, the stiffness, and it will automatically calculate the design force using the response spectrum. So it depends on what type of analysis you are doing. Well, it depends on how good your bricks are. So someone has also written that IIT Gandhinagar, they have constructed G+3. But IIT Gandhinagar building, the story is different. I have been there, I've seen. So the property of bricks was so poor there that they had to actually develop their own brick manufacturing factory inside the campus. So they manufactured their own bricks by adding fly ash, by adding some admixtures, and then they improved the compressive strength of individual brick units to about, I think, I don't remember exactly, but about 12 to 15 MPa, or maybe 10 to 12 MPa. So how high you can go, it depends on the strength of the bricks, the quality of the bricks available. In India, we have gone up to G+3. There are many other cases in other countries where people have constructed 6 stories buildings. because the type of bricks is very good in other countries. Okay, now you tell me how deep is the focus? It is about 10 kilometers, 5 kilometers, in some cases 1 kilometer, that is the depth of the focus. In some cases it is even 70 kilometers. Okay. Now these earthquake waves are traveling this much distance before it reach the structure. Now compare this 15-20 kilometers with a few meters of your soil which is interacting with the structure. Do you really think that that will, I mean, change anything? That is not going to change anything. And during the first vibration itself, there will be some gap between the soil and the structure, which again refills, and then again it vibrates. So it is not proper to assume that we don't consider the soil below. We have to consider the entire structure. Like I said, if you think that this member contributes to mass and stiffness, you have to consider it in the analysis. There is no way you can leave it. See, R is a direct function of ductility, right? Redundancy, ductility. In masonry, the failure is by brittle shear. The failure is in a brittle shear mode, right? So obviously the R value, the response reduction value for masonry will be much less compared to the reinforced concrete, simply because the material is like that. Now, if you look at the code, IS 1893, if I remember correctly, it has the value of 1.5 only for masonry structures. Comparatively, if you design reinforced concrete structures with ductile detailing, the value is 5. Okay, so it is about 3.5 times less compared to RCC. But if you can provide some reinforcement in the masonry, you can further increase this R value. So for reinforced masonry building, R value can be equivalent to, it can be as good as 5, as high as 5. Thank you all. I would like to hear some of the participants. So maybe from tomorrow, 5 questions verbally that we can do. Rather than just these people writing here and then looking for which to answer, which to not. Maybe top 5 questions you can ask them to ask verbally. Okay. Thank you. We'll see you tomorrow.
Thank you so much, sir.
Yeah.